Okay, so we're going to look at complex equations and then the conjugate roots theorem. So generally starting off, just looking at complex equations and kind of specifically kind of quadratic equations. With equations and complex numbers, we typically use kind of z as a variable. Okay, we've kind of seen that already, that we call our complex number z. Z's usually the variable instead of x squared, so we would write our quadratics as az squared plus bz plus c. If we're solving a quadratic in complex numbers, we generally go straight to the formula because we're expecting to have a square root that results in a negative number under the square root, so that we're going to be using our I so that we get our complex number answers or solutions. So say we're going straight to the formula here, so it's minus b, so 6 plus or minus b squared, so minus 6 squared, minus 4 by 1 by 27, all over 2 by 1. And again, we're just kind of simplifying everything down. So 36, 4 by 27 gives me 108, all over 2. So 6 plus or minus, let's see, 36 minus 108 is 72, minus 72 over 2. So let's look then. Square root of 72, we can rewrite that as 6 root 2. So because of the I, it's going to be 6 root 2 I, because of the minus 1, I should say. Which means that Z is 3 plus or minus 3 root 2 I. And we can rewrite over here just to write our answers out. 3 root 2 I, and Z is 3 minus 3 root 2 I. Okay, so using the formula in the same way, making sure we're subbing in for A, B, and C as per normal, but just we end up with that 6 root 2i there, running low, instead of the just getting an answer there. So that's where we kind of include that I part and get those complex number solutions. If we're given the roots, we can make use of this result that we have from algebra, which is that x squared minus the sum of the roots, x plus the product of the roots, is equal to 0. And this could be really, really useful with complex numbers specifically because the roots themselves are kind of a bit more long. So here, like we have 3 plus 5i, 3 minus 5i. So it's not like it's just the root is 3 or the root is 7 or something like that. So we have kind of extra things to think about. So if we use this formula here, z squared minus the sum of the roots, so 3 plus 5i plus 3 minus 5i, z plus the product of the roots, so 3 plus 5i by 3 minus 5i. And that's going to be equal to 0, I suppose. So z squared minus, let's work out about this middle bit, that gives me 6. Z plus multiplying this out, we get 9 minus 15i plus 15i minus 25i squared. Sorting this out, we get plus 9. It's plus 9 plus 25. To get z squared minus 6z plus 34. Okay, as our quadratic equation there. So again, fairly straightforward, just a matter of kind of practicing it with our complex numbers there as opposed to our other examples. We've two quadratics here. I'm going to leave those as practice questions. Again, you're just using your formula, you're just using your quadratic, your minus b formula, subbing those values in as we did there in that first example. I want to prioritize, I suppose, the conjugate roots theorem here. And this is a very particular example that can be really useful for us with our complex numbers. So if we're looking at these solutions, and we kind of saw in the two we did above, the solutions often work out to be conjugate pairs. And what we mean by that is that we have one answer and the other answer would be the conjugate of the first one. So say what we had there in that question, the roots were 3 plus 5i and 3 minus 5i, so conjugates of each other. And this can kind of be generalized then into the conjugate roots theorem. And that says that if we have a polynomial, so a z to the power of n, whatever n is, it doesn't matter. So if it's z squared, z cubed, whatever it is, if we're given a root of that polynomial, and if all the coefficients are real, then the conjugate is also a root of this equation. So the important thing there is that this part here, all the coefficients have to be real. If we don't have real coefficients, then this theorem won't hold and it won't be true anymore. But the theorem can be quite useful for us. So say here, show that 6 minus 2i is a root of this equation. So to show that something is a root, so let me see. So if we want to show root, we want to sub in. So we're going to have 6 minus 2i cubed minus 15, 6 minus 2i squared, plus 76, 6 minus 2i, minus 120. And we want that to be equal to 0. So let's just have a look over to the side here maybe. So 6 minus 2i squared, what will that give me? 36 minus 24i plus 4i squared, which is 36 minus 24i minus 4, which is 32 minus 24i. So 32 minus 24i. If we were to do 6 minus 2i cubed, that would take our previous answer, and we're going to multiply it by 6 minus 2i. Let's just take my calculator over here. So 32 by 6 gives me 192. 192 minus 64i minus, let's see, 24 by 6 is 144i, and then plus 48i squared. And if we kind of simplify all of that down, 192 will take away 48 because of the I squared there. We get 144, and then, minus 208i. Okay, so let's try and sub all these bits in and see if that kind of works out for us. 144 minus 208i, this bit here, 144 minus 208i minus 15 by 32 minus 24i, plus, let's multiply out this part, so 76 times 6, 456, 76 times 2 minus 152, yeah, minus 152i minus 120. Okay, and let's just multiply all of this out again. So 144 minus 208i, 15 times 32 gives me 480. So minus 480, 15 times 24 minus, so plus 360i plus 456 minus 152i minus 120. Okay, and we can just kind of consider the numbers and consider the I parts here and see, do we end up with a nice kind of answer for ourselves? So let's have a look. So 144 minus 480 plus 456 minus 120, and that gives us 0 in the real parts. And then in the imaginary parts, we have 360i, take away 208, take away 152, and that gives us 0 there as well. So we get 0 equals 0, so that proves that that is a root of the equation. Now we're asked to find the other two roots. So since the coefficients are real, if we look back at our equation, the coefficients are all real. That means we can say that the conjugate is also a root, which is 6 plus 2i. So 6 plus 2i is also going to be a root of the equation. And because we know that, we can work out the quadratic that would have both of these as a root of the equation, using the same kind of quick formula that we used earlier. So sum of the roots by the product of the roots. So z squared minus 12z plus, let's just work out this, so 36, yes, 36 plus 12 minus 12 minus 4i squared. So we get z squared minus 12z plus 40 as our quadratic, first of all. And then because we have a cubic here, we're just going to divide our quadratic into the cubic to see what answer we get. So doing some long division then. So z cubed minus 15z squared plus 76z minus 120. Okay, we're dividing our quadratic into our cubic here. Get z cubed minus 12z squared plus 40z. Okay, and just following through with our long division as per. So minus 3 and plus 36z, we can bring down our minus 120, plus 3, or sorry, minus 3 I suppose. Minus 3 gives me minus 3z squared plus 36z minus 120, and they will subtract to give me 0. So my roots are z equals 6 minus 2i, z equals 6 plus 2i, and then z equals 3. Okay, coming from my factor there at the end. So I suppose important to note there why we can use that conjugate roots theorem, and it's because the coefficients were real. If we look through that example that we have here, now I know I've kind of blanked it out, but we can kind of follow along. So if we're showing that z2 to the power, or z equals 2 minus I is a root of the equation, and then show that z conjugate of z is not a root of the equation and explain why. Well, just considering the coefficients there that we have, we can see straight away that the conjugate would not be a root because we do not have real coefficients. If we wanted to show that it wasn't a root, we would substitute in and show that we don't get a value of 0. But the explanation as to why is because we do not have real coefficients for that polynomial. So we're going to pick one or maybe two of these exam questions to have a look at. So let's look at this first one here. z1 is 1 minus 2i, and z1 is a root of this equation. Find the other two roots of the equation. So we can say that we have real coefficients, which means that the conjugate 1 plus 2i is a root. Okay, same as before. We can find the quadratic that would have both of these as roots by using that little trick from earlier. So multiply the roots at the end. So z squared minus 2z plus, let's see, 1 minus 4i squared. So z squared minus 2z plus 5. And then we're going to be dividing that into the cubic equation to find the last remaining root that we have. So let's have a look. So z, so it would be 2z, so 2z cubed minus 4z squared plus 10z, and subtracting those values gives me 3z minus 3z squared plus 6z minus 15. I'm going to be multiplying by minus 3 minus 3z squared plus 6z minus 15. And that's going to subtract to give me 0. So we'll have 2z minus 3 as a factor, which means z is 3 over 2. And my other roots, of course, we had already kind of established z is minus 1 over 2 and z is 1 plus 2i there as well. Okay, and those are my three roots, and it's well important to lay those out. We've kind of said this already, but general exam technique, if you're asked for three things, if you're asked for the roots, lay out the roots that you're looking for. Okay, and we lay out all three. We were asked to find two, we might as well just lay out all three of those. I'm going to skip over that second one. I'm going to leave that as one for you to do. Same idea as what we've been looking at. You have the solutions already as well. And we look at the third one here. So 1 plus I is a root of this equation. Find its other root in the form m plus ni. Okay, so here we're kind of pulling back some ideas from Algebra 1. So we have two ways to approach this question. So I'll write them down here. First is simply solve. So we could solve it using the quadratic formula. So if we were to solve the equation using the quadratic formula, that would give us the two roots. We're asked to find the other root. That would be a way for us to solve the equation, find the two roots, and then yes, we could kind of already have one of the answers and get the other answer. The other way is to use this m plus ni that they've kind of hinted first. This is the other root that we're going to have. So we already know if we have this other root, we can create an equation as we've done previous questions, and then we could compare that with the equation that we have there. So let's have a look at that one. So remember, we're using that same rule we've been doing here all along, where if we have the two roots, we can create a quadratic that has those two roots by getting minus the sum of the roots plus the product of the roots. We're going to use this m plus ni as one of the roots, and the other root is the 1 plus I that's in the question. So let's have a look at that. Minus 1 plus I plus m plus ni. Okay, then the product of the root here, so 1 plus I by m plus ni. Let's have a look then. So 1 plus I plus m plus ni. multiplying out here, we get m plus ni plus mi plus ni squared. And we can kind of simplify. God, race against the clock. So we can simplify down. So we get 1 plus I plus m plus niz plus m plus ni plus mi minus n. Okay, minus n coming from the I squared part there. So now what we're going to do is we're going to be comparing different parts of this equation. Okay, we're going to be comparing different parts of this equation with each other. Okay, so say we were to take the middle part here. Say we were to take this whole middle part. So what's in front of z here and what's in front of z here. We would say that minus 1 plus I plus m plus ni is equal to minus 2 plus I. Let's just multiply out this left-hand side. Minus 1 minus I minus m minus ni is minus 2 plus I. And the last thing we're going to do is group together things that have and things that do not have an I part. Okay. So C plus, we see minus 1 minus n. Okay. So let's look at the real parts first of all. So that's these parts here. So we can say minus 1 minus m equals minus 2, and that's going to mean that m is equal to 1. And comparing the imaginary parts, we have minus 1 minus n is equal to 1, and that's going to mean that n is equal to minus 2. Okay, so we're comparing the real and the imaginary parts there. So now, as I said, there is another way to do that one. So we will just finish by, I suppose, writing out the root there. So it would be 1 minus 2i. The other way we could approach that one is to solve the equation using our minus b formula. So it would be minus b 2 minus I plus or minus square root of b squared minus 4ac all over 2a. And again, just simplifying down as best we can. So we get 4 minus 4i, I squared giving me minus 1 there. And minus 12 plus 4i all over 2. And what we're kind of expecting to happen is for kind of our I parts to kind of simplify down here, I suppose. So we get 3, so minus 9. Yeah, minus 9. And on the bottom here, oh, sorry, on the bottom here we just have 2. So z is equal to 2 minus I plus or minus 3i over 2. So taking the plus or minus version, 2 minus I plus 3i over 2, or 2 minus I minus 3i over 2. So we get 2 plus 2i over 2, and 2 minus 4i over 2. So we get that z is equal either 1 plus I or 1 minus 2i. Obviously, we already knew about 1 plus I, so our answer is the 1 minus 2i part. So I suppose there's a fair bit in all of that. The key things there that we've looked at, I suppose, are the quadratic formula and applying that to our complex solutions. So getting that square root of a negative number and then that including the I part, and that's kind of how we end up with those complex roots. And then the second key part that you need to know of is this conjugate roots theorem. So you need to know that it is a thing and what it means. It means that the roots of our polynomials tend to come in conjugate pairs, but you also need to know that it only happens when all the coefficients are real. So if we have non-real coefficients, as we saw in one of the examples there, if the coefficients of an I part, then the conjugate roots theorem does not hold. So you need to just know what it is and when it applies, and if it doesn't apply. So if it doesn't apply, you need to know why it doesn't apply. So those are kind of the key things, I suppose, from that whole section.